The following content has been provided by RWTH Aachen University.
All right. Now, when the guys, Harrell and these folks came up with the UML, they were like, transition networks are cool, but not powerful enough. Petri nets are very powerful, but our brain hurts when we use them. So they were looking for something in the middle. And that's called state charts. And state charts are something you should definitely know because they are part of the UML specification. So pay attention because this is a notation you will most likely find in some kind of design documentation at some point. I use an example here of a simple TV control panel. This is an extremely simple TV control. It basically kind of looks like this. It has a button that says on. It has a button that says off. It has a button that says reset. And it has a button that says mute. Plus, it has a button that's called select, S-E-L. And that basically is basically it's for couch surfing. It's like next channel up, next channel up. And when you're at the top channel, it goes back to channel 1. And this TV only has 4 channels. It's a poor old school TV. So that's all you can do on your remote. And how are we modeling this as a state chart? Well, state charts are extending state transition networks. So they basically are similar to state transition networks, but they add a little to it. What they add is, first of all, hierarchy. As you can see here, we have here a single state. And here we have a whole little network, or all of this. And this is put into a box. And there are transitions from the state to this box, and from the box sort of back to the state. So we can basically put state transition networks into other ones. We've already done this before in hierarchical SDNs, but state charts also do this, and they specify a little more precisely what that means. The second thing, and this is the really powerful part about state charts, is concurrent subnets. We here have one subnet that deals with sound, and here we have one that deals with the channel, almost like Petri nets. And they are running in parallel. So they are both little finite state machines that actually are executing in parallel. They are divided by this little dotted line, which is basically the AND operator, meaning that these two things are supposed to happen concurrently. We also have specified that if we are in such a compound state where there is like lots of stuff going on inside, the whole state machine inside the state, we have something that is called an escape, which means no matter what state I'm in here, if the user presses off while this state machine is in any of these positions here, it basically leads to the standby state. Okay? So that's as if I had connected this individually to this one, and this one, and this one, and this one. That's the escape mechanism. And finally, there's a history marker. Because the question is, when you enter a compound state that has lots of stuff going on, where should the little state transition network inside it start running? What's the start state? If it's always the same one, then we have this problem of remembering history, like we had with the help system. That's why the state chart notation allows you to mark nodes with a little h. First of all, if we don't do that, we just basically put this little black dot next to one state. That's the same as double circling it, which basically means when this state transition network gets activated, start in this state. That's exactly what this black dot here indicates. It's as if this was double circled. But if we want the system to remember where it was last time it was running, we write a little h next to that arrow. So what this means is the first time this state transition network gets activated, it starts in state 1, which basically means when you unpack your TV, turn it on the first time, it will start on channel 1. But if you then turn it off and turn it back on later on and enter this compound state again, the channel will remember where it was last time before it was deactivated by pressing off. So it will go back to, for example, channel 3 if that was what you were watching, which is actually kind of a nice user interface thing. If you watch TV and you turn it off in the evening, you turn it back on in the morning, it still is on the same channel. That kind of makes sense, right? You don't want to go back to channel 1 each time you turn your TV on. So that's explicitly modeled in the state chart to say this history marker basically models the smartness of the TV to remember its channel even when it's turned off. The sound doesn't have that, which basically means if you turned on your TV and entered these two parallel running state machines, the sound engine, if you like, the sound state machine here, basically turned the sound on. It starts in the sound on state. Now, you may mute your sound and later turn off your TV. But the next time you turn your TV back on, what should happen? You're a designer now, right? You need to think about like what should be going on when I turn on a TV that was muted before it was turned off. And these designers said, we want to ignore the mute, we want to cancel that, and we want to turn the TV back on with the sound turned on. Because most likely when somebody turns the TV on, they actually want to watch TV and hear the sound and not have it muted. Although, maybe a bar or something that always wants the sound muted would not want this. They might want a different kind of TV functionality. But at least we're discussing the design decision here, right? And it's explicit in the state chart. It's clear what's supposed to happen. So those are the main extensions that state charts allow. They're pretty powerful because you can model design decisions like the sound being on when you started. And you can also see things in these state charts that would bother you, like, for example, going back to channel 1 each time you turn on your TV. The new things are, first of all, the compound states that lead to like substates with the entrance marker and the history marker for smarter behavior, and the AND notation that says that we can actually have two state machines running in parallel. And so we model the sound with this one and channel with this one, and they both are happening at the same time, kind of like Petri nets.
This content was provided by RWTH Aachen University.